Amirthavalli, Associate Professor from the Department of Petroleum Engineering. In today's session, we are going to learn the properties of reservoir fluids. The first property we will learn is the crude oil gravity. That is, we would have learned that density is nothing but the mass per unit volume. That is, the mass of a unit volume of the crude at specified pressure and temperature will be termed as the density. As we all know, the density can be expressed in terms of lb per feet cube in terms of FPS unit. Then what is the difference between density and specific gravity? Specific gravity will be defined as a ratio of the density of the oil to the density of water. That is rho naught by rho W, where rho naught is the density of the oil in lb per feet cube. Similarly, rho W will be the density of water in lb per feet cube, and both the density of oil and the density of water will be measured at 60 degree Fahrenheit. That is the standard condition. So what is a unit for your specific gravity? Specific gravity is a dimensionless unit, dimensionless quantity, because the numerator and the denominator will carry the same units. So what is the density of water? We would have seen in SI unit the density of water is 1000 kg per meter cube, but in terms of FPS unit, the density of water is 62.4 lb per feet cube. Another important way of expressing the gravity is API gravity in petroleum industry. What is this API gravity? API stands for American Petroleum Institute. It is the preferred gravity scale. It is relating to your specific gravity. So API gravity is equal to 141.5 divided by specific gravity of the oil minus 131.5. API gravity will be set in terms of degree. This API gravity will help you to classify the type of crude. Either it is a light crude, medium crude, or extra heavy or heavy crude. So the API gravity of the crude oil will range from 47 degree API for lighter crude to 10 degree API for heavier asphaltic crude. So as I said about API gravity, we can see that for a lighter crude, the API gravity will be above 31.1 degree, and for a medium crude, the API gravity will fall between 22.3 to 31.1 degree. The heavy crude oil will have API gravity less than 22.3. Extra heavy, which is referred to as the bitumen, it will have the API gravity below 10 degrees. We can see an example how to calculate the specific gravity and the API gravity. You see that calculate the specific gravity and API gravity of a crude oil system with the measured density. Density was given in the problem 53 lb per feet cube at standard conditions. So the first thing we have to do is we have to calculate the specific gravity. As we have learned in the earlier exercise, that specific gravity is nothing but the density of the oil divided by density of water at standard condition. So density of oil was given to be 53. As we know, the density of water in terms of FPS unit is here 62.4. So when you divide it, the specific gravity comes to the value of 0.849. API gravity, they are asking you to calculate the API gravity. API gravity, we know that it is 141.5 divided by specific gravity minus 131.5. So it is 141.5 divided by the specific gravity value, which we have found out to be 0.849 minus 131.5. So it comes around 35.2 degree API, which says that it is a light crude. That's what we have to infer. Next, we will see the next property, that is your bubble point pressure. So bubble point pressure is defined as the highest pressure at which the first bubble of gas is liberated from the oil. The bubble point pressure is a function of, it is dependent on gas solubility, gas gravity, oil gravity, that is API, and your temperature. So we have learnt about gas gravity, oil gravity, that is degree API, as well as the temperature also we'll know. In the next session, we will learn what is gas solubility. Next property which we should know is the oil formation volume factor. Oil formation volume factor will be represented by the symbol V0 It is nothing but the ratio of the volume of the oil plus the gas which is present in the solution at the prevailing reservoir temperature and pressure to the volume of the oil at standard conditions. This B naught value will always be greater than 1 or it is equivalent to 1. We can represent it as mathematically B naught is equal to B naught base P comma T divided by B naught at standard conditions. As I said, B naught is the oil formation volume factor in terms of BBL per STB. STB will stand for your stock tank barrels of oil. P naught P comma T will be the volume of the oil under reservoir pressure and temperature in terms of barrels. V naught SC will be the volume of the oil measured at standard condition in terms of STB. This B naught, that is your oil formation volume factor, is also dependent on gas solubility, specific gravity of the gas, the specific gravity of the oil, as well as the temperature. We can see from this diagram that oil formation volume factor changes with respect to pressure. So, as the initial reservoir pressure gets decreased till its bubble point pressure, what happens is the oil volume increases. Why does the oil volume increases? Due to the expansion, the oil volume increases. Similarly, your oil formation volume factor also increases and reaches a maximum at B0B. So it reaches a maximum at the bubble point pressure. After the bubble point pressure, there is a decline in the oil formation volume factor because the gas gets liberated out of the oil. Since gas is lost out of the oil or liberated out of the oil volume decreases, hence your oil formation volume factor also decreases. So when it reaches to when the pressure is reduced to the atmospheric pressure and the temperature to 60 degree Fahrenheit, the B naught value becomes equal to 1, which we can see from the graph. The B naught value at the standard condition, it comes back to 1. Next, we will see the next property, which is called the gas solubility. The gas solubility will be represented by the symbol R suffix X. It is nothing but the number of standard cubic feet of gas which will dissolve in one stock barrel of your crude oil at certain pressure and temperature. The gas solubility of the natural gas is also a function of pressure, temperature, API gravity, and the gas gravity. You can see from the diagram, the gas solubility is dependent on pressure. So, as the pressure is reduced from the initial reservoir pressure to the bubble point pressure, we can see that the gas solubility line remains horizontal because there is no gas which is evolving out of the oil. Hence, the gas solubility remains constant at its maximum value of RSB. So, at the bubble point pressure, we can see that it becomes RSB. Below the bubble point pressure, when the pressure starts to decrease, the solution gas will be liberated out of the oil. As the solution gas is liberated out of the oil, the gas solubility will start to decrease with pressure, because we know that gas solubility is how much amount of gas is dissolved inside the oil. So the gas starts to come out of the oil and the gas solubility decreases with pressure. That's what we have to infer, and the gas solubility will carry the unit SCF per STB, that is standard cubic feet of gas per stock tank barrel of oil. So we have learned about the properties of the reservoir fluids. In the next class, we will work out the problems using the basic concepts which we have learned regarding the gas solubility, oil formation volume factor, API gravity. Thank you all.